welcome back to another day of notes, and hope that you enjoyed your break. What we're going to talk about today is 16.4, Green's theorem. And so Green's theorem gives the relationship between a line integral around a simple closed curve C and a double integral over the plane region D bounded by C. So what Green's theorem is going to allow us to do, it's going to allow us to find the line integral over a simple closed curve C, and makes our work quite a bit easier. And so let me just read through this and then I'll explain if there's anything else. In stating Green's theorem, we use the convention that the positive orientation of a simple closed curve C refers to a single counterclockwise traversal of C. Thus, if C is given by the vector function r of t as a less than or equal to t less than or equal to b, so as a goes to b, then the region D is always on the left as the point r of t traverses C. So here you have two examples, one with the positive orientation where it's going counterclockwise, and then you have one with a negative orientation where it's going clockwise. All right? And if we are going in a negative orientation, put the wrong arrow there, then we'll just have to change that and make sure that we go positive, and there'll be an example of how or when that occurs. So Green's theorem, let C be a positively oriented piecewise smooth simple closed curve in the plane, and let D be the region bounded by C. If P and Q have continuous partial derivatives in an open region that contains D, then the integral of P dx plus Q dy is equal to the double integral of the partial derivative of Q with respect to x minus the partial derivative of P with respect to y dA. And so basically what that simple closed curve is that when we have a region, we start and end at the same point, but we don't cross each other. So we don't cross ourselves, and it's actually closed. If we have this region, that's not a simple closed curve because it's not closed. If we close it, now it's a simple closed curve. And again, we want to go, when we're doing Green's theorem, making sure that we go in the positive direction, which is counterclockwise. Now, this is what I mean when it crosses itself. If we have a curve and we do this and we get back to that part, we see how we cross ourselves there. That's not a simple closed curve. And so therefore we cannot use Green's theorem exactly on that, because we have now two regions. And so instead of having one region, we have these two regions. All right, so that's what a simple closed curve is. And so all we're doing is we're taking our function, or taking our integral P dx plus Q dy, and instead of integrating it with just that, finding our line integral, what we're doing is we're going to, define it as a double integral by the difference of the two partial derivatives of Q and P with respect to either with x and y. And it makes our work a lot easier, because a lot of times when we're finding line integrals, we have to split it up, use parametric equations, and it can take a lot of work. And you'll see in our next example how using Green's theorem really minimizes our work. So Green's theorem in circulation curl. So we're really going to focus on curl next section, but Green's theorem in circulation curl form asserts that the circulation of a vector field around a simple closed curve C is equal to the double integral of the scalar curl of the field, the Riemann sum of the paths around the little boxes of the vector field over the region enclosed by the curve. So when computing a line integral along a closed path, we indicate the integral. So I want you to notice right there. So I'll just write it up here. So we have the integral. Then when you have a circle inside that integral, that means that we're, going on or going along a simple closed curve. So that right there indicates that we're over a simple closed curve. When you have that symbol, you have that circle inside your integral. It means that we're going along a simple closed curve. So it's nice. So when you see, this notation right here, we know, oh, hey, I can use Green's theorem here to find the line integral. So, what is the value of the scalar curl for a conservative vector field? Now, again, remember, if we're going over a conservative vector field, what we have for our vector field is going to be the partial derivatives of that function that we're originally doing. And so, when we're going along a conservative vector field, we have an independence of path. And when we're thinking about that, and if we're starting at a point and then finishing at a point, maybe you remember this from last class, it's going to be 0. All right. One way to look at that is, we talk about line integrals, and a good application of line integrals is going to be that it represents work. And so, this is work done along, a vector field, and in this case, on a closed path. Well, the work done on a conservative vector field is going to produce 0. There's not going to be any work done because we start and finish at the same point over our conservative vector field. Another application you see that algebraic is, remember, how could we tell if we're dealing with a conservative vector field or not? We know that the partial of Q with respect to x is equal to the partial of p with respect to y. And again, what would the difference of that be? And that told us if we were dealing with a conservative vector field, because the second derivatives, taking one with respect to x and the other with respect to y, should equal each other. That tells us that we're on a conservative vector field. And if I'm taking one to the other side, then the partial of q with respect to x minus the partial of p with respect to y is going to produce 0 if we're working on a conservative vector field. So we can also use Green's theorem to show that we're on a conservative vector field just because of the difference and how we're able to compute what the line integral is using Green's theorem. And again, Green's theorem is a pretty long proof. If you'd like to see that, I'll put that up on YouTube. It's just let me know if you want to see it, because just right now is a very, very busy time. So I don't know if I'll be able to produce that till probably next week. And by next week, we'll probably be finished with Calc 3. All right, I'll stop the video here and then